So 18 see, this is August 25, isn't it? Table at the right shows the cost to send an express mail package using U.S. Postal Service. Does this table define a function? What do you think? Okay, it does define a function. So A, it's a function. Is it therefore a relationship? Because a function is defined as a relationship that has a certain kind of thing. So if it's a function, it's a relationship. Given x equals 0.5 pounds, what is y? So what would you say y would be? 0.5 pounds. So would it be $10.70? Do you notice that the range is 0? It's less than x, which is less than or equal to 0.5 pounds, right? It's in that range because it's less than or equal to. So this is $10.70. See that? Everyone agree? Okay, 20. This, we're using this function. F of x is equal to 5x minus 4. And this function says f of minus 2. So what that's saying is that you take the f of x function, but in every place an x appears, what do you put? -2. Then you evaluate it from there. That makes this a -10, 5 times a -2, -4. So this is a -14. So f of -2 is equal to 14, -14. So that would be 28. This is using q of x, q of r equals r squared minus 4. So they want to know q of 4. So wherever the r appears, you square it and you put 4 in place of that. And 4 squared is 16 minus 4. So q of 4 equals 12. If you look at 36, here we're using the function h of p equals 3p over p plus 2. And they want to know h of minus 3. So every place the p appears, we're going to put minus 3. So that makes the numerator minus 9 and the denominator minus 1. So that's a plus 9. H of minus 3. It says S of t equals p cubed minus 3p plus 4. So S of 2, we replace wherever there's a T, we replace it with that 2. So then S of 2 this is 8, 2 cubed, minus 6, plus 4. So S of 2 is 6. Oh, 44. 44 says that you have this G function of T equals 9 minus 2T. And they want to know what G of a minus 3 plus H minus G of minus 3. Now I'm going to add some brackets here so that we do it right. It's G of minus 3 plus H minus G of minus 3. So we're going to take the G function and we're going to evaluate this one first. So wherever there's a T up here, we're going to put minus 3 plus H. So I'm going to do 9 minus 2 and wherever that T was, I'm going to put a minus 3 plus H. And it's this minus right here. And I'll bracket that. And now the G function says 9 minus 2, and wherever the T is, I'm going to put minus 3. Now I'm going to expand what's inside here. Look at this. So back up here. This is going to be 9, and I run that minus 2 through there, so that's a plus 6 minus 2H. And that's a minus. And then this is 9 plus 6. Minus 2 times a minus 3. So now that first one is 9 plus 6 is 15. 15 minus 2H and minus, and this is 50. So then I drop the brackets. 15 minus 2H. Now that minus, that bracketed plus 15 is a minus 15. And a minus, or plus 15 minus 15 is 0, so this is minus 2H. So that function evaluates to that. This thing right here. Will evaluate to that down there. That's a little bit trickier. You got to make sure that you hold your brackets together and do things. So, next, 46. It says an airport administrator have tendency to price airport parking at a rate that discourages people from using the parking lot for long periods of time. The rate structure for an airport is given in the table at the right. Evaluate this function. So A. So if you have T equals 2.5 hours, what's that going to be? What's going to be the cost? Does it cost $6.50? See that? Because that 2.5 is in the range from 2 to 4, right? The B part, T equals 7 hours. So what's the cost there? What range is that one? 10? $10. Okay, so that's how you do those problems. Any questions so far? 50. Want the domain and the range of that set of ordered pairs. So the ordered pairs 2, 6, 4, 18, 6, 38, 866, and 10, 102. So it's a set of those ordered pairs. The domain, it's the set of first numbers of those ordered pairs. So it's 2, 4, 6, 8, 10. So it's these numbers right here. Domain. The range, it's the set of all second numbers. 6, 18, 38, 66, 102. So that's all of these. Oops, I don't contrast them very much. These elements. Range is that way. I'm going to look at '58 just to show you something about this. 58 is range and domain. So the set -8, 0, -4 and 2, -2 and 4, 0 and -4, 4 and 4. So the domain. Now it's all the first elements. minus 8, minus 4, minus 2, 0, and 4. The range. And that's going to be second ones. 0, 2, 4, minus 4, 4. So we go 0, 2, 4, minus 4. But when we come to that second 4, we don't put it in there because it's already in there. That's what I want to exemplify. You only put a value in either the domain or range once. If it repeats in the ordered pairs, you don't repeat it in the range and domain. That's all. That's the only reason I did this problem. Says exclude from the domain values that don't make the problem correct. Now, what happens is there's actually only two things that can make a domain be limited. One is, and that's the one that they're looking at in this problem, is if you have a variable, domain variable, in the denominator. So you would have a fraction, and I want 60 exemplifies this. G of x equals 1 over x plus 4. Now, first of all, the domain is always defined as all real numbers. X is an element of the reals. That's the way you put it. And then it's except where the range is not defined. Now, notice that this thing, the x values will not only, in this particular problem, the x values are in the denominator. What can you not divide by in the real number system? What makes an undefined number? When you try and divide by 0, right? Because 0 into any real number is not infinity, it's undefined. Now, what you do is, you see there's a variable right here in the denominator. So what you want to check, what value of x would make that denominator 0. And that value is minus 4. So from your domain, you have to say minus 4 is not in it. Cannot be a minus 4. So the domain then is x is an element of reals, and x cannot equal minus 4. There's something called set builder notation, that if you write x such that defines a set. This is read x such that x is an element of the reals and x is not equal to minus 4. That little straight line is just such that. And that's called set builder notation. Your book probably won't use it, but you will come in contact with it over time. In college algebra, you come in contact with it. Here, g of x equals 4 minus 2x. Is there a variable in the denominator? No. So the domain is x element of the reals. Now, I will tell you that there is another problem that you will incur when you get into particular college algebra where the domain is restricted, and that's when you have the square root, let's just say x minus 4. Now, what can you not take the square root of? The square root is defined as a number such that when it's multiplied by itself, gives you the number under the radical sign. So when you have the square root of 1, what do you have? Obviously plus 1, right? 1 times 1 is 1. But is it minus 1 also? Minus 1 times a minus 1 is a plus 1. So the square root of 1 is plus or minus 1. Plus 1, minus 1. What's the square root of 4? 2 and minus 2, right? Both numbers. So it's 2 or 2 or minus 2. So usually you'll say plus or minus 2. Well, the next one that gives you an integer answer is what? 9? And that's plus or minus 3. Now, what is it you can't take the square root of? What number multiplied by itself gives you minus 1? No real numbers. That introduces a whole new number system called the imaginary numbers, and which leads to another new number system called the complex number systems. We're only dealing with the reals. So in the real number system, you cannot take the square root of a negative number. So this thing is x minus 4 has got to be greater than or equal to 0. And x has got to be greater than or equal to 4. That's the only thing that can be under that radical. You know, I'm just telling you this because there's only two situations in the real number system where you have to limit the domain. One is when you're taking the square root of variables under the radical sign, and the other is when the variables in the denominator. You, in this section, only are dealing with variables in the denominator. So, 64, the domain, the answer is all real numbers. 70, f of x. So you're not going to have to worry about square roots. This thing, is there a variable in the denominator? No. So domain x element of reals. 73, h of x minus 2, x plus 2 is a variable in the denominator. Yeah, it's x plus 2 is the denominator, it has the x in it. So you go x plus 2 equals 0, x equals minus 2. So the domain x is an element of the reals, and x is not equal to minus 2. If you had a number line and you were going to graph this solution, then what you would do, what it would look like, if this were 0, then what you would do is you'd go down here at minus 2, you would circle it, indicating that it's not in, and you'd say every other number on that real number line, except minus 2. Now the reason that we can draw a number line and represent it by the real numbers is just a real unique thing about real numbers. Because real numbers are called a dense system. That is, between any two numbers, how many numbers are there in the real number system? Infinite number of them. And you can prove it. I mean, when you get further in mathematics, if you ever do, to advanced mathematics, you have a 2-page proof to prove that there is an infinite number of numbers between any two numbers. And the simple proof is take any two numbers, 1 and 2, add them together and divide by 2. That gives you halfway, right? That's between 1 and 2. Now take 1 and 1.5, which is that number you would get, and add them together, divide by 2, and you get halfway between those two numbers, right? How many times can you repeat that process and always get a number? An infinite number of times. Now take a number line. Take a line that long and get halfway, and then halfway, then halfway, then halfway. How many times can you do that? Infinite number of times. Now there's a one-to-one correspondence between the real numbers that you did and that particular point on that number line. And that's a 1.5 page or 2-page proof. But that's why we can say the real numbers, and we can draw a number line, and it's dense, and it's there. That's why we deal in the real numbers in the real world, and that's the nice thing about real numbers. 78. G of x. G of x is 3 minus 5x. Now what they want is they say find the range for the given domain. So the way you want to do this is they're giving you the domain. And they're giving you these values. Minus 2, minus 1, 0, 1, and 2. And you want to present an answer that says the range values are some set of numbers. The way to do it, if you can't do it, if you don't see it other ways, let's do it this way. Put in an x, and then over here put a g of x. Because this is a function, so it is a relationship. So technically you can say this is y, right? Now then, for every one of the numbers, x is minus 2, minus 1, 0, 1, and 2, find the corresponding g of x or y value. So you take the minus 2, put it in to 3 minus 5 times a minus 2. And that's going to get you 3 plus 10, 13. Then put 3 minus 5 times a minus 1, and that's going to be 3 plus 6 is 9. Then put 0 in. 3 minus 5 times 0. And 5 times 0 is 0, so this is 3. Then go 3 minus 5 times 1. So that's 3 minus 5, which is a minus 2. Then put 3 minus 5 times 2, And it's 3 minus 10, which is minus 7. So this range values are 13, 9, 3, minus 2, minus 7. If I did my process right, that should be my answer. So that's the range values. That's what they're looking for you to solve. Any questions? 86. So here, my g of x is 4 over 4 minus x. And they have the domain it's the set minus 5, 0, and 3. Notice they have left off the one that would, they've left off 4, because 4 couldn't be possible. You'd have to say under 5. Now they want the range values. And so what you want to do put your x in the g of x, and put for x put minus 5, 0, and 3. And then do 4 over 4 minus a minus 5, right? Well, that's 4 over 9. Correct? So then take your function 4 over 4 minus 0, which ends up with 4 over 4, which is 1. Then do 4 over 4 minus 3, and that's 4 over 1, which is 4. Any question about that? So now our range values is the set 4 ninths, 1, and 4. That's how you do those problems. I'll do 92, real world example. Give a real world example of a relationship that is not a function. Is it possible to give an example of a function that is not a relationship? If so, give one. If not, explain why it's not possible. Okay, so the real world example that I gave, remember at the beginning of class, I had myself first as a teacher, and then I said you as a student, right? That's an ordered pair. Myself, her as a student, that's an ordered pair. Myself, Joshie as a student, that's an ordered pair. Now, that's a relationship. Me first, the student second. But is that relationship a function? No, because there's more than one second element, right? With me first. If you turn that around and put the student first and me second, then for every x there's one y, and that is a relationship. You can make a relationship that is not a function by taking, if you have more than one brother or sister, you can say you to each one of your siblings. That's not a function. But if you take your siblings back to you, that is a function. If you take your father to each of you and your siblings, that's a function. But if you take your siblings back to your father, that's a function, right? For every x, there's one y. So you have to check and make sure that it works. I guess I'm going to back up. Your father to each one of your siblings, that's not a function, because every x has more than one y associated with it. But when you throw the children back to the father, it's a function. So you can think of other examples. Now, what about that second question? Is it possible to give an example of a function that is not a relationship? Well, I'll tell you that's not possible, because a function is defined as a relationship that has a special characteristic. So every function is, first of all, a what? A relationship. So you can never give a function that is not a relationship, because in order to be a function, it has to, first of all, be a relationship. Does that make sense? Every relationship may or may not be a function. It has to meet special characteristics. But every function must first be a relationship. So functions can always be expressed as relations. 94. Find the set of ordered pairs x, y determined by the equation absolute value of y equals x. So let me just write this down. Every function, remember that's shorthand for function, is first of all a relationship. Therefore, all functions are relations. Not all relations are functions. They have to be a relationship that has a special criteria. 94. Find the set of ordered pairs x, y. So this is the relationship. And they're saying, is that relationship, does it express a function? So what you want to do to try to figure this out is do your x, y's. And then it's saying that the domain is an element of this set, 0, 1, 2, and 3. So put in 0, 1, 2, and 3. Now, if x is 0, y must be what? If x is 0, y's got to be 0, right? If x is 1, well, y can be 1, right? But if x is 1, y could be minus 1, because the absolute value of minus 1 is 1, isn't it? So 1 for x, minus 1 for y. Now then, if x is 2, it's obvious y could be 2, right? I guess less than obvious is if x is 2 and you do absolute value, you could have minus 2, right? So 2 minus 2. And likewise for 3, you could have absolute value 3 equals 3, and you could have negative absolute value 3 equals 3. So this is 3 and 3, and 3 and minus 3. Now, So y can be an element of 0, 1, 2, 3, minus 1, minus 2, minus 3. Or the ordered pairs are this: 0, 0, 1, 1, 1, minus 1, 2, 2, 2, minus 2, 3, 3, and 3, minus 3. Now from our discussion, you can see that this particular set right here, you have repeated x's that have different y's associated with it, not a function. Okay. Says the graph of the right. Well, let's do 96, 98. Let's do 98. A. It says the graph at the right shows what an industrial psychologist has determined to be the average percent score P for an employee taking a performance test 2 weeks after training begins. Estimate the scores of the employee would receive at the test when A T equals 4 weeks. So what's the score going to be at the end of 4 weeks? %? B, T equals 10 weeks. What's the score? 100%. So if you were scheduling the training, what would you schedule the training for? If you wanted your team to be totally competent, it'd be what? 10 weeks, right? And so what you do is you would look at this thing and you'd say, well, do I want, how, you see it, you get pretty close there at 4 weeks, you get 90%. And you'd say, what's good enough? What training, what number of weeks of training? Because at 4 weeks, you're more than doubling the training to get to 100%, right? And you notice at 3 weeks, you're just under 90. So the question is what's practical? If the average score is 90, that means some people are getting 100 and some people are probably getting 80, right? So what you have to make the decision. Am I shooting for, and it's if you're hiring from the general population, you would have a bell-shaped curve of learning. And that would mean that 2/3 of the people would fall within one standard deviation. And then you figure out the standard deviation and you say, is this good enough? And you do a cost analysis of it. Okay, I didn't hand that 2 and 3 out, so let's see how.